Welcome to Excel 2013 Statistical Analysis video number 31. Hey, if you want to download this workbook or the PDF files, click on the link below the video. Hey, we're in Chapter 5. We're going to talk about discrete probability distributions. And we already know a little bit about probability distributions, not only from Chapter 3 when we did frequency distributions and relative frequency distributions, but also from last chapter. Now we have to define some terms before we can jump over to Excel and create some probability distributions. Hey, our first term is going to be random variable x. Hey, this is going to be a numerical value resulting from a random experiment that by chance can assume different values. Another way to describe a random variable, a numerical description of the outcome of a random experiment. Now, it's a description because sometimes we can have customers coming into a store. So we're counting 0, 1, 2, 3. Hey, that's easy to tell it's a number, right? Weight of a cereal box. That's another one. It's easy to tell that this is a number. This is weighing ounces. But what about this one? The experiment's going to determine defect or not defect. How in the world are we going to get a numerical description for that? Well, we're going to assign it 1 or 0. Now, we're going to have two types of random variables. Let's scroll down. We've got to talk about being polite. You have to be very discreet. No, discrete random variable, that's x. That just means we're usually counting. Discrete numbers have gaps. So 1, 2, 3, or 1.1, 1.2, 1.3. This is in contrast to a continuous random variable. This is weighing boxes of cereal or timing things. So it depends on the measurement instrument. The way you think of it is here's 1, here's 2. There's lots of numbers in between there. It depends on the instrument you're using to measure. All right, so discrete may assume either a finite number of values like 0, 1, 2, 3, or an infinite sequence of numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You could think about an infinite sequence like how many people are showing up to your store in 5 minutes. Well, there could be 0, there could be 1, there could be 2, there could be 3. It could go on forever. Well, theoretically forever, right? So we're going to leave it as an open-ended infinite sequence of numbers. Examples of discrete: customers coming into the store. We could have 0, 1, 2, 3. Scores for a dancer, right? 0, 0.1, 0.2. Even though this doesn't seem like counting, it is. We're 0, 0.1, 0.2, et cetera, all the way up to 10. We could also have product quality like defect equals 1, not defect equals 0. Now, the discrete random variables, what we're going to be talking about in this chapter. Chapter 6, our next chapter, we'll talk about continuous random variable. May assume any numerical value in an interval or collection of intervals. Depends on the measurement instrument. Weight of cereal. Time between customers in line at Disneyland. Percentage score on a test, or even money. Now, money may seem like it's discrete, right? 1 penny, 2 penny, 3 penny. But there's lots of situations where money depends on the measuring instrument, or you have fractions of pennies. Now, what we're really after is probability distributions. And a probability distribution is just a description or presentation of how the probabilities are distributed over the values of the random variable. If you think back to last chapter, we did frequency distributions with relative frequency and cross tabulation. There, we just had all of the percentage for some categories, and they had to add up to 1. So that's a description of the probabilities distributed, in our case, in this chapter, over a random discrete variable. Now, discrete probability distribution, the same thing. A description, presentation of how the probabilities are distributed over values of a discrete random variable. Now, we can have 3 different ways that we can describe or present. Here's our table method. Last chapter, we did this. We had an experiment, flip a coin 3 times, and the number of tails was defined as a success. We could get 0, 1, 2, or 3. We calculated all the sample points and then calculated the probabilities. This is the table form. Now, from this table, we can do things like, what's the probability of getting 2 tails and 3 flips? 0.375. How about the probability of 2 or more? You just add those two together, so it's 0.5. We can also present or describe all of the probabilities across the values of our discrete random variable with a chart, right? 0, 1, 2, 3, and then the height represent the probabilities. We can also use a function like, and that's our binomial function. Looks big and scary, but we will see that it kind of makes sense in terms of calculating a particular event later in this class. Now, that right there is awesome because you can't always, like this example here, list all the sample points. So if we flip a coin 10 times, I don't want to list all of those sample points. That's where this formula will come in and be really quite easy in compared to creating this by hand with all the sample points. Now, that's a discrete probability function, and the discrete probability function will be defined as, hey, f of x. That's what this author uses. I use p of x. I like p because it means probability. Both of these are perfectly all right. And in almost all of my handouts and Excel workbooks, I'll list them both. But I like p of x to describe discrete probability function. Hey, this p of x or f of x, that will provide the probability for each value of the discrete random variable. So here's one of the values. Here's the other value. Each one of these probabilities can be calculated with this function right here. Now we want to scroll down and talk about the methods of assigning probability. Hey, well, just as you might suspect, last chapter we learned about classical, relative, and subjective. Well, you can use those 3 methods for creating discrete probability distributions. Hey, classical, if we had an experiment, roll 1 die. These are our only outcomes. This would be our random variable x. We'd list it here and assign probabilities. Now notice, this is one of those cases where they're all the same. This actually has a special name, discrete uniform probability distribution. And the probability function is 1 divided by the number of values that the random variable may assume. Now, relative method or relative frequency method, we go from past data. And we'll actually create this frequency distribution from scratch later in this video. But our experiment is count the number of restaurant banquet rooms used in one day. There are 4 banquet rooms, so the possibilities are 0 all the way to 4. We did a sample over the last year and got these frequencies. We calculated these relative frequencies. They add up to 1. Each individual one is greater than 0. So we have our relative frequency distribution. We can use these as probabilities. Now, relative frequency method, when lots of large data is used, is called an empirical discrete distribution. Now, we can use this to make predictions. The probability that we're going to use 2 rooms, 0.41. Probability that we're going to use 2 or 3, 69%. The final method, subjective, we have little past data, and we do not have equally likely outcomes. In this example, a sales example, usually there's lots of data. We can look at past records to calculate number of compressors sold at a compressor shop. These are big DeVilbiss compressors. So sometimes they don't sell any. Sometimes they sell 1. Usually they sell 2 or 3, 4 or more. We list our probabilities, but since we don't have past data, the sales manager just estimated from memory, did not analyze past data. In essence, this was their first year of operation, so there was no past data. People do subjective, but notice it meets our objectives, adds up to 1 each individual probability greater than or equal to 0. Now, the big advantage of frequency distributions, as we've already mentioned in this video and last chapter, once you have a frequency distribution, it's easy to calculate probability of a variety of events. So we could ask the probability that number of compressors sold is less than or equal to 1. We simply look up here, add 0 and 1. Probability that we sell 2 or more compressors, we look up here, add 2, 3, and 4 or more. Now the steps for building a discrete probability distribution, we've done some of these already. However, we will have a step 1 here. We'll define our random variable, build the frequency distribution, calculate the relative frequencies, check the requirements, create a column chart. If desired, we'll do that a number of times to visually portray our distribution. Remember, with discrete in this chapter, we will not have our columns touching. And then use it, make predictions. Now I have some examples here in our handwritten notes. In this example, last chapter and our earlier example in this video, we did success equals get a tail. Here it is success equals get ahead. So we've defined that as our experiment. Hey, but it comes out looking almost the same. These numbers are upside down when you're counting heads, right? But we list our sample points, calculate our probabilities, and this is our table we're going to use to make predictions. There's our column. Our next example, hey, we're going to create a discrete probability distribution, and you can read through this. This is our Italian restaurant with banquet rooms. But I want to scroll down here because we're going to talk about 2 important formulas, and then we'll go over and calculate these in Excel. Expected value. That's the term they often use when we have frequency distribution. It just means we need to calculate the mean. They will use mu, which is a Greek letter to represent this. I'll tend to use expected value. But notice x times probability. You do all of them and then add them up. We actually did this as a weighted average back in chapter 3. We could think of this as the mean, the weighted mean, the expected value, long run average. And guess what? The value does not have to be a value that the random variable can assume. So for this example right here, here's our number of banquet rooms on any particular day. Well, the actual x value is 0 to 4. We got an average of 2.18. That's perfectly all right. That is our average. But remember, it's just a weighted mean. Super easy. We'll use SUMPRODUCT function. Hey, and standard deviation for a discrete random variable, guess what? We're going to take x. That's our random variable. So in this example, it's 0 to 4. Each one of those, subtract our expected value, square it, and we'll multiply it times the probability. Then take the square root. That'll give us the standard deviation. Just like our mean gives us central location or one value that represents all the values, standard deviation will give us variation or dispersion. It will tell us how fairly our mean represents our data points. Now here's the longhand method, and we will do it over in Excel. So let's go over to Excel and calculate not only mean and standard deviation, but we'll create our frequency distribution, relative frequencies for our discrete random variable. Now here's our situation. Isaac's Italian restaurant has 4 banquet rooms. And they're wondering about how frequently we use all 4 or how frequently we use 0 rooms. Not only would it help us with our staffing, but it helps us to predict using probability. If it turns out we hardly ever use 4 rooms or we never use the rooms at all, then we need to make some adjustments. Now here's the data we collected over the last year. Control down arrow. It's basically every single weekend except for a few holidays. Here are the number of rooms used. Now I'm going to go ahead and use formulas. They give me more freedom in terms of making charts. And we don't even have to extract a unique list like we've been doing with pivot tables and advanced filter. Because guess what? Number of rooms is 4. So what are the actual number of rooms used in a given day? Well, it's 0, 1, 2, 3, or 4. That's it. Now we can count using our COUNTIFs function to get the frequency. COUNTIFs, the criteria range. I'm going to click in the top cell, Control-Shift down arrow, F4, comma, and then left arrow to get our x, our discrete random variable of 0. That's a relative cell reference. Control-Enter, and copy it down. We get our counts. We come down to the bottom, Alt equals, and Enter. Now we can come over and calculate our relative frequencies. Equals relative cell reference, the count for our random variable 0, divided by the total count, F4 key to lock it. Control Enter, and copy it down. Come down to the bottom. We got to check our rule. We got to check our requirement. Alt equals, and Enter. So that's got to be equal to 1, and each one of these have to be greater than or equal to 0. Could we have actually gotten a 0? You bet. What if we never, ever had a 0 value? Then that would come out 0, even though it's a possibility for our random variable. Now here's our formulas up here. X times probability, each one of them. Here's our X. So we're not dealing with frequencies. We're dealing with our actual X value. So the X times each one of the probabilities, and that will give us our expected value or our mean, and then our standard deviation calculation. Now the cool thing about starting off with this example and learning like this is we can go ahead and actually test these formulas. We can calculate the mean and the standard deviation from our source data and see if these formulas estimate closely or not. Now let's go ahead and calculate our expected value equals sum product. Guess what? I'm not even going to do it the longer way that we learned back in Chapter 3, because this function is made perfectly for this. It's as if Excel and the functions are actually built perfectly to do statistics. We're going to take our range, our array 1 of x's, comma to get to the next argument, and our array here. Remember, sum product. The product part takes the two columns, 0 times 0.02, 1 times 0.21, etc. So it multiplies the individual numbers in each one of those columns. Remember, the two columns have to have the same dimensions. If one of them is a different size, you will get an error. Some product can't do that. So we have our two ranges, close parentheses. Now, what does the sum part do? Once it multiplies, it then adds, and we get 2.8. Now, I'm going to go ahead and test our formula, right? Remember, x's times the probability, see if it actually works. I'm going to run the average function, which calculates the mean on our original data source. Control-Shift down arrow, Shift-Enter to put that in the cell and jump up. And it gets exactly the same thing. Now let's calculate our standard deviation longhand. And I am actually going to do it longhand once. And then I'm going to teach you a single cell formula, because it's not too hard, especially if you in this class you're learning Excel for the first time. When we learn that, if you just remember this formula or have this right next to you, then it's easy to do. But let's do it. Remember, we're trying to calculate the deviations between our x and our mean. So I'm going to come here, equals our random variable minus our newly calculated expected value, or our mean, F4 to lock it. Control-Enter. Remember when we did this in Chapter 3, numerical measures for standard deviation and variance, when we did our deviations and we came to the bottom, we added them because they always added up to 0. Alt equals, it's not going to happen here. Enter. And the reason why is because we do not have our original data points. We only have our x here. So we'd actually have to do it on all of the data points. So that's not going to work. But this will get us to our correct answer for variance and standard deviation. Next, we have to square that. Equals relative cell reference, caret 2, Control-Enter. And copy it down. Now we have to take deviation of random variable minus our expected value squared and multiply it times the probability. So equals relative cell reference times relative cell reference for our probability. Control-Enter and copy it down. Now this whole time I've been talking variance and standard deviation. This one right here, and I'm going to caret 2, that is, we learned earlier, this symbol right here is standard deviation. Usually we start with variance and get to standard deviation. But check this out. That whole thing is going to be variance. So right here, I'm going to actually show you how to insert that symbol, I'm going to go up to Insert and way over in Symbol. And you might have to search around for it in Symbols. And there it is right there. If you use it a lot, it's down here in Recent. I'm going to double click and enter that. You could also click Insert. I'm going to click Close. So there it is. And I'm going to put caret 2. That's our symbol for variance. Now we can add these all up, and that's the variance. As we talked about in Chapter 3, the problem with variance is that it's not in the same units. Because when you square in this step right here, you also square the units. So it's better to do our standard deviation equals square root. And boom, there we go. 0.9206. So we have a mean of 2.18 rooms. So on average, on any day, we're using 2.18 rooms with a standard deviation of almost 1 room, or 0.9 rooms. Now let's scroll down and see what happens if we calculate from our original data set. Now, this may or may not have been a sample. In our case, it was every single number for a year. But because it's the original data set and we go through these calculations, it's actually like trying to calculate the standard deviation of the population. So that's the function we're going to use right here, STDEV.P. Simply highlight, Control-Shift down arrow, Shift-Enter, expand the column. And it gives me exactly the same answer. So both of these formulas, properly labeled expected value and variance, both of these will actually, from our frequency distribution, get us the correct numbers. Now I want to show you the single cell formula. I'm going to actually pull this down here because it helps as you create it. Now I want to look over here. Notice I had to take, in essence, a whole column, enter F2, enter F2. You see this blue one over here? But it's like the whole column minus a single value. So when you have a relative cell reference and an absolute, enter, and you're doing the whole column, it's like I'm taking this whole column here and subtracting one cell. So when we do our formula in a single cell, I'm going to highlight the whole range. And we'll use SUMPRODUCT, which you can handle those ranges. The whole column of x's, subtract our one expected value, then square it, and then multiply it times the whole column of probabilities. So watch this. Equals, and we're using SUMPRODUCT. Now, array 1, that's going to be that little bit right there, times, remember what SUMPRODUCT does. We can take array 1, comma, array 2. So watch this. In parentheses, because we have to force the subtraction before the squaring, I'm going to take this whole column of x's, subtract one single value. And by the way, close parentheses, let's highlight. I'm going to highlight this whole thing and do a trick just to show you, as we're building the formula, what each part equals. I'm going to hit the F9 key. And is that exactly equal to that column? Whoa, it is. Control Z. When you F9 to look at a particular formula part, be sure to undo it with Control Z because you don't want to hard code it in there. So I've simulated that whole column in our cell. Now I'm going to, at the end here, caret 2. And let's see if when we highlight this, boop, F9. No way, it got exactly that column. That is amazing. Control Z. So now I have this column. And then what do I do over here? I took relative cell reference in each one of these times each one of these. So I'm simply going to comma array 2. This is our probabilities, or our relative frequencies. Close parentheses. This will give me variance. Enter. Exactly the same as that. What do I have to do? I have to take the square root, so I wrap the square root function around it. Control Enter. So when we're given a frequency distribution, which in the textbook, the homework, and in the working world, a lot of times you already have your frequency distribution. You created it a long time ago, and you're using it all the time. Anytime you need the mean, you can simply do boop, x's, boop, relative frequencies. And then standard deviation, we'll take, well, the whole column of x's, subtract the mean you just calculated, square it, and that'll be the first array. And then the second array will just be from your discrete probability distribution, your relative frequencies or probabilities. Now, we've done this. We've created this from our raw data. And now we have our expected value and standard deviation. Now we can use this information. All right, so what's the probability that we get one or fewer rooms? I'm going to use the sum function here, alt equals. It totally guesses wrong, but now I'm pointing up here. Remember, I need x equal to 0 or x equal to 1. I'm using my adding rule. These are mutually exclusive, so I simply add 0.23. That's the probability on any particular day that I'm going to use one or fewer rooms. What's the probability of using 2 or 3 rooms? Alt equals, I have my frequency distribution. I just, 2, 3, highlight the two probabilities. Those categories are mutually exclusive. I'm using my adding rule, enter. 0.69. Now, what's the probability of x greater than 0 or days when we actually use the room? I could come over here and alt equals and highlight everything that's not 0. But I could also, especially if it was a big frequency distribution, go equals 1 minus and use our complement rule. That is totally cool. Now, that was our example for Isaac's Restaurant. Let's go over to the sheet PD3, and we have another great example. Hey, this is data collected number of arrivals at Dick's Hamburgers on 45th Avenue in Seattle on Saturday noon lunch during a 1-minute period. That means we want to look at the random variable x arrivals in 1 minute. Now, if you've never been to Dick's Hamburgers in Seattle, at some times it is just swarming with people. People are just like flocking to there. So this is a big list. There's a lot of collected data, control down arrow. So this is a tally. One observation over a minute, 14 people came. One time, 12 people came. 2 times they observed during a minute, 11 people, and so on. Control up arrow. 0 is the smallest, and you can see there's a bunch of recorded times when 0 people came during a 1-minute period. So we want to build a frequency distribution, 0, 1, and then copy this down. Now, all the way down to 14. Now we can do our frequency equals count ifs. Control Shift down arrow, F4, comma, left arrow, Control Enter, and I'm going to copy it down. Wow, so it looks like they counted 28 times when 0 people came during a 1-minute period. 102, only 1 person came. 191, 2 people. But look over here, right? So 4 people coming every minute, 266, et cetera, all the way down to, there was one time where 14 people came during 1 minute. We can add all these up. Alt equals, enter. Now we can calculate our relative frequencies equals 1 cell to my left divided by the count, F4 to lock it. Control Enter, and copy it down. Alt equals, got to see if our 2 requirements for discrete probability distributions are met. Hey, yeah, they all add up to 1, and each one of them is greater than or equal to 0. So it looks like the probability that we have 4 people showing up during a 1-minute period is about 20%. And we could calculate whichever other event we want, greater than or equal to 4, less than 4. Let's come over here and calculate our mean. Now, we could calculate this from our source data. But again, most of the times you're just given this, and we want to calculate a mean. No problem. We know weighted average. Sum product. I'm going to click the first array. Not frequency. It's the x's, comma, and our relative frequencies. close parentheses, and enter. So our mean is almost 4 people per minute. The variance equals sum product. We're going to take all of our x's. We're going to subtract the mean we just did. I have to put parentheses around it. I have to come back here because those parentheses at the end has to be orange. I love that color coding. No, I accidentally clicked out. OK. Now, very carefully, I'm going to try and click right at the end. Sometimes when that happens, you get into trouble. It's easier to complete it up in the formula bar, but I'm going to be risky here. This is still array 1, caret 2, comma, and then array 2, the probabilities. Close parentheses. There it is, just like our formula. The x's, boom, minus the expected value, boom, caret 2, and then our probabilities, the whole column. Control Enter. So, the variance is huge. If we take the square root, and it's 1.9. So it looks like the average number of people arriving in 1 minute is about 4 with a standard deviation of almost 2. Now, later in this chapter, we'll talk about this special distribution. It'll be called a Poisson distribution. But we can, from our discrete probability table here, calculate whichever probabilities we want. Hey, what's the probability during a 1 minute period that we'll have 2 or fewer people? Alt equals, it totally guesses wrong, 2 or fewer, and enter. So 24%. How about the probability that we get 3 or 4 or 5? Alt equals, then I'm going to add up 3, 4, and 5. Enter. So 57% that we're going to have a bunch of people arriving during a 1 minute period. Hey, what's the probability greater than 0? That means the probability that someone shows up during a 1 minute period. Alt equals. You could highlight all of these, escape, but I'm just going to go equals 1 minus that 0 and enter. So there's a about 98% chance that someone's going to show up every minute. All right, so in this video, we talked about building discrete probability distributions. We also talked about calculating the mean, the variance, and the standard deviation. When we come back in our next video, we're going to look at this mean and standard deviation calculation for an accounting and finance example. All right, we'll see you next video.